All right, guys. Cool. Welcome to this fun packed edition of live training featuring regression modeling. My name is Michael Fertoni. I'm one of the customer support engineers here at Alteryx. Usually, I help you guys find any errors that happen when you guys are working with your workflows. But for the next hour, I'm going to be your teacher in regression modeling, and specifically how it's integrated with Alteryx. So just a heads up, I don't want to get too much into the theory and math behind it all. It can kind of get pretty complicated. But I want to just focus more on, the general idea of how regression is used and how it's used specifically in Alteryx. Okay. So today's agenda, pretty straightforward. I just want to go over quickly we'll go over the upcoming trainings and any specific workflow background knowledge you kind of want to make sure you have before taking this. And then we'll get into the actual details of the module and then some extra support things if you need any future help. And of course, if you guys have any questions, feel free to post them in the chat. I should be able to see them and I'll try to answer them as we go along. Yeah, don't want to have you guys want to hold off until the very end for questions as it can get sometimes pretty intense. So yeah. Next, we have more predictive training in the next 2 weeks. Stay tuned for those. Also pretty super fun. And then a bunch in March, which is, as you can see, to be decided. Yeah, that's it. And for those of you who are new, I assume you were at the community to get here, but if not, haven't really explored, you can look at the URL at the bottom, community.alteryx.com. It's a great way to share ideas, post questions and answers and stuff. It's kind of like your own Alteryx support group with everyone else who's super enthusiastic about data analytics. We're here to help and make sure all of you can get the most out of our software. So background for today's training. Hopefully you guys all attended Sydney's pre-predictive training last week. It goes about exploring your data and what kind of variables you have. Just really making sure you know what kind of data you have. It's not just like, I downloaded this, now let's get going. You actually explored it a bit. Because, depending on what data you have, some models won't actually be applicable, and some of the other ones could fit right in. It kind of limits your pool of options, which actually makes predictive analytics less intimidating and easier to work with, because you only know you can only use these two. So definitely make sure you know your data. Now, specific to regression modeling, I'll kind of go over the basics of each model we'll work with. But the general idea is that we're kind of trying to find out the slope that best fits our data. So whenever new data points come into play, we can just apply those new data points to our model or slope, and that can help us predict what we want to know. Not too complicated. So with that being said, we're going to use a use case of understanding restaurant expenditures for our linear regression example. So, we've cleansed our data and we know everything about it. So the first thing we want to do is identify our dependent or target variable. In this case, we want to find out how much money does a household spend on restaurants. And on the flip side, we also want to know which of our variables kind of influences this amount of money that's being spent. It could be like size of the household, income, things like that. And these would be known as our independent or predictor variables. Hence, they help us predict our target. And so, how would we do this? Kind of like a process you can see on the right. First, we build our model with past data. That kind of tells our model, kind of relates the predictors to our target. We see how much they influence it. And next, we do kind of like a brief scoring so we can do some post-analysis on our models to see, which model would be the best for us to use. And next, we want to identify which of the predictors we've selected, which ones are actually useful. Because for instance, let's say we have religion in our first model, because we're not actually sure if that influences spending or not, but it could, so let's put it in there. But after our first, run through, we kind of see that it's not really needed, or it's just giving us misleading information, so we can just throw that away. So that's what we kind of are looking for when we are at the identify stage. And then finally, once we have our full final model, we predict how much money we have with any new data. Hopefully that's pretty simple. Let's see now, some key concepts. So yeah, just now we can get into the whole, weeds of it all. I believe the best way to teach regression is to just go over, simply an example. We can bypass most of the theory and math, like I said, so we can see more of it in its application. So our example and use case for today will be linear regression, which is usually the simplest type of regression. I'll talk about logistic in the sense of how it differs and how it applies differently depending on what data you have. And then carrying on from our linear model, we'll use the stepwise and nested tool to see which variables are most optimal and which final model we'll want to use before we end up scoring the model, how we would get our newly predicted results. And again, I just want to make another note out there. Predictive analytics can get pretty intense and kind of wordy with specific jargon, so I'll try my best to limit that and not get too indefinite theory, and limit this to, like I said, predictive analytics and its use specifically with Alteryx. Oh, that was weird. Linear regression. So what does it do? Predicts probability of a continuous variable. You guys may be wondering, what is a continuous variable? I kind of just see it basically as just numbers. So if you were to think of, let's say in this example we have cost, like amount of money. Our data points are $2,000 and $3,000. If we put that on a graph and we connect them with a line, we know what's in the middle. It's like 2,500, 2,700, but if we have something categorical, which is what I would consider more strings. So for instance, we do eye color. Someone has blue eye color and someone has green. We connect the dots there. We don't have anything in between, it's not continuous, it's very discrete. It's just one after the other. So that's what we mean by continuous, something that has a continual range. Makes sense. So with our actual linear regression model tool in Alteryx, there are 3 outputs that you get. One is the object, which is right here, out of the O stream, which I'll show you guys shortly. Yeah, this one is kind of used just for further analysis. Like this is where the whole data stream in that model is actually stored. The other 2 outputs is the reports. The first one is kind of like a PDF version. You can kind of just see what you have, and kind of just look at it first to see if you like it or not. And then there's an interactive one, which is basically the same thing but more interactive, as the word suggests. And then just a quick note about logistic and why it's a bit different. So if you guys can see, just the tool image, linear is a line, nothing too complicated with it. But logistic can get more, I'm just going to say like curvy, it doesn't follow a straight path. And with that, we can only predict probabilities of binary categories, so yes or no's, ones and zeros. So for this, our use case with the, how much money a household can spend, this won't be very applicable because what we want to find out is an amount of money. So it's not really yes or no kind of thing. And the outputs are the same thing as with actually most of our predictive tools. You have the object that you can use for further analysis, and then 2 reports. So just to do a quick demonstration of what linear regression is, I use just a simple data set in Excel that I made up. So let's say calories is our predictor. We think calories influence how much weight someone is. So we plot them in our graph. They're right here. and then we make our trend line. So our trend line is actually what the regression or the linear regression model tool does. We are looking for this line that kind of matches all of it. And if you want to imagine, back in high school when we did linear algebra, our formula for the line is y equals mx plus b. X and y's, x's being our targets, our x's being our predictors, which would be our calories. And then our y's being our weight, being our target. And then what we're kind of looking for is our slope, which, how much that predictor influences the target. So, when we do our linear regression, we get this line, and, that's kind of what we do. So for any new data point we have, let's say our next calorie point is, what's on my head? Let's say 3,300. All we would do is plug 3,300 into this formula, and we would get our new y. And I don't feel like doing math, but I hope you guys can understand that. I don't know. Let's see, what would it be? 160 something? I have no idea. Sure. And then that would be our new line, and that's how you kind of predict it. But of course, the one thing we always want to check is how accurate this line is if we need to do any more adjustments. But that's generally the idea of how linear regression works. So let's move on to Alteryx in our example. So this is our data. You guys can always go to the community article for the live training to download it if you want. But for now, this is what we have. I'll pull up the results so you can actually get a better idea of it. So these are just the IDs. And this is what we're actually going to want to predict. This is how much money is spent. It's called food away. Neat, I guess. And then these are all other variables that could or could not have influence on it. So usually, before you do any type of predictive modeling, you kind of want to do this create samples. Because if you use your whole data set when testing your model, you don't want to overfit it specific to that data. So you only want to give it a little bit, or you can give it most of it, what's called our trained data, and then you use the rest of it to kind of test it out to make sure it's viable and not so specific to your trained data. I hope that made sense. Again, post questions in the chat. If it doesn't, I can more than happy to elaborate. So the general practice in predictive modeling is to do 80% for our testing, or 80% for our training, and then we validate using 20%. So using this create samples tool, that's what we generally do. E has our 80%. So we'll feed that into our linear regression tool. Again, we do have two versions of the tool. If you right click and you ever want to switch back and forth, we have 1.1 and 1.0. For now, we're going to use the old version, the 1.0, because it's simpler. And yeah, I don't have to talk about all the details and get carried away like that. So, like I said before, simple configuration. We're looking for our target. That's what we put in here. And then what do we think influences it? In this case, we have our income, our age, family size, the oldest child, and if it's an urban household. And then we kind of run. We just hit run, right? That's our object that I said. And then our report is what you can see here. Now, this can get, there's a lot of information here. You don't really have to know all of it in the beginning. Some kind of stuff you would need to know is, first off, is our formula. So it's all in R syntax. I don't want to talk too much about it, but this is what you're kind of looking for. So food away, which is our target, our Y, equals x1 plus x2 plus x3 plus x4 plus x5, and those x's indicate our predictors. So that's kind of what we're visually kind of looking for and what we see. And so moving away from that, we go to our coefficient table, and this is, if you can imagine, our y equals mx plus b kind of format. This is our b, our intercept, right? And then this is our m's for each x's. So, for instance, with income, income influences our line by this amount. So if we have income is 100,000, it would be 100,000 times this number plus our intercept, and that's what would be our new y value or our new money spent. But we have values for all of them. So you kind of attach this estimate to its x1, x2, x3, its corresponding formula value. So yeah, you can see that the oldest child, ranged from 12 to 17, actually has the highest influence on our line. So you would initially think that this is the most significant and this is very important, but that's not exactly true. Next thing you want to look at is our p-value, which kind of tells us how significant our coefficients, or sorry, not our coefficients, how significant our predictors, our variables that we chosen are. Oh crap, I missed the, is it different for us to generally use? So let me make this one point real quick. Sorry guys, I got a little sidetracked. So yeah, our p-values is how significant our variables will be. So generally, a general rule is, again, trying to avoid the crazy math that goes along with it and all the statistics. But the closer to 0 it is, the better. You kind of want it below 0.05. And as you can see with all of these, income is the only one that is very much below 5 or 0.05. So it's the most significant, and these not so much. So yeah, we might want to remove these in the future, which we'll get to. And then the next thing we want to look for is, how accurate our model is in general. If you guys have used Excel, you may be familiar with the R-squared values. And it ranges from 0 to 1, 1 being perfect, meaning every data point that we would have is on that model line. So in this case, 0.21, not very good, not very good at all, but that's okay. We can move on. So yeah, those are the main kind of things you want to look at when looking at the report, to kind of see how good your model is and if you want to make any more adjustments. So someone asked, is it different for Alteryx, or is this a general rule that I use? I am unsure for which point I was making when this question was asked, but in terms of this lesson, most of my, I guess, ideologies and theories are in general. It's not so specific to Alteryx. Let's just say Alteryx is the application. And so yeah, I try to keep it simple and not get too complicated. Oh wait, I see what he was asking with Alteryx. So yes, I believe it was probably in reference to the create samples tool. That is a general rule of thumb for any predictive analytics anywhere. So whether you're coding raw in R or in Python, or you have another software that uses predictive analytics, 80-20 is the general split that you would want to do. Yeah, so moving on from linear regression. So we have our model, we have our object. Let's see, I talked over the results. So next we would use our stepwise tool, which helps us determine which ones are these best predictor value or variables. And the configuration is pretty simple. It just has these two options, search direction and adjusted fit measure. For search direction, you generally will go backwards by removing the variables, and then you find this goodness of measure for field. It's kind of arbitrary. Again, I won't get into it. And the other way is backward and forward. It's more accurate, but it's a slower process. And so if you have a lot of data, your model is huge, you have a lot of variables, and you're short on time, you may not want to use both backward and forwards. But generally, backwards and forwards is the option you would want to do. And then for adjusted fit measure, we have the AIC and BIC criteria, which again, it depends on what you have. There are links to look into it. Again, I don't want to get too much into the details of it. But yeah, general rule is to just use AIC. And then it comes out with the same kind of report that we have here. So let's go back to Alteryx and check it out. So as you can see, we use both backward and forward, and we use the AIC. Our linear regression object here out of the output. And then our report is here. Again, looks very similar to the linear regression because it is. It's just the submodel of our linear regression tool. It just has less variables in it, right? So if you want to compare it, I'll just click back and forth. But for now, you can see our formula now just holds income, which is what we determined was the only significant variable. So food away equals income. We look at our estimate now. That's actually generally the same. Our p-values are the same. And our R value should be similar. So it's 0.2106 here, 0.21 with the adjusted. And if we check back to our linear regression tool, it's the same thing. More or less. This is slightly better. But the reason why you would want to use a stepwise tool is if you look at the size of the object, it's less intense. You know, it's only 180 bytes, and the object here is 330,000 bytes. So it's a lot smaller, and it'll be easier to work with. So you can do a lot of processing a lot faster. So let's check anything else we want to compare with. Yeah, so that's basically it. So it, found that all of these other predictors that we had weren't significant at all, and it took the one that was. So that's generally what the stepwise tool does. So now that we have, our stepwise object, and we have our linear object, we kind of want to make sure, which one is better. I do have a question came in that was asking about how do you do regularized linear regression? Again, I can get to that if we have time. That's just in terms of, well, I'll just show you what she meant by that question. So if you go to linear regression tool in our new one, you can use regularized regression, and you kind of range between two types of settings, which in itself could be another lesson. But yeah, I'll talk to that if we have time. So going back to our example, let's see. Anyway, to improve the result, adjusted R squared in this case, like transformation for the data. So improve the result of our R squared. With what we have, so what you can try to do if you wanted to improve that R squared value, you could try to include other variables to see what's important. Again, depending on the size of your data, so let's see, our total data here is only 1,400. So it's not super expansive. If there was a lot of data, so basically in this case, you could kind of change with the sampling percent because it might and change the random seed. It might get you different results, but it would be around the same anyway. What this would kind of tell you though, if it is so far off, is that linear regression kind of doesn't match your data too well. So you might want to explore other options. Another question, what's the random seed for in the create samples? So the random seed, it's kind of just if you ever wanted to repeat the same type of sampling, the same data that was used for this 80 and 20. So that way I can always call, random seed 1 is this specific kind of data. If I change it to 2, it'll be a different 80-20 mix. This will be a different 3 will be a different 80-20 mix. But yeah. So yeah, so I think I'm good with questions for now. So yeah, let's continue on. So we have our stepwise, sub-model of our full linear regression model, and we kind of want to make sure, how is it worth kind of using the stepwise model or linear regression model? Which one is more complete? Okay. So that's why we would use our nested test. Basically, it compares two models, one that is a subset of the full model. So in our case, we had our full model had these variables in it, and then our reduced model had just our income in it. So it's a perfect use of the nested test, something that's nested inside of it. And I just want to clarify, it's not, you don't want to use the nested test for something of different models. So you wouldn't use the nested test to compare a logistic regression model to a linear regression model, or a decision tree to a linear regression model. It is the same type of model, just different, a reduced set of variables of that original one. So let's go to the nested test. It's nice. It doesn't really require any configuration. You put the full model here, the nested model here, or the reduced model here, and then your original data that you used for both. And then you get a report. And same thing, we see that the p-value is not too high, so it's not really too significant that one is better than the other. But for our case, for when we do our final scoring, we're going to use stepwise tool, or the stepwise object, because it's smaller, and the difference in the R-squared and the accuracy isn't too great. So moving on to the score tool. Basically, it kind of appends a score. It does our, our analysis with any new data that we have. So whenever new X's come into play, we can use a score tool, and it'll find our new Y's. And again, there's other options to use, which if we have time, I might get into if someone is curious. But for now, I'll leave that out. You really just only need to add it in, and then this is auto-filled. So yeah, you put in your object that you want, which is our stepwise object, and then our data stream here is our 20% that we got from here. So now that we have our full model that we validated, we can use our 20% to do it. So someone wanted me to go over the nested test a bit more. So what number am I looking at when I choose the model? So the point of the nested test is to kind of see how significant one model is to the other. In this case, since our p-value is greater than 0.05, as a general rule, we see that there's no kind of great significance in either of these models. They're that means they're generally the same. They'll perform similarly. The only reason that I would be using the stepwise object is if you look here, and this is probably specific to Alteryx, but also in general, because our R-squared values are so similar. So if you look at our linear, it's 0.214, and here it's 0.210 or 2.211. Because they're so similar, the speed we can get from getting rid of 6 extra variables and its effect on our final result won't be that significant. So that's why I'd prefer to use the smaller model because it's easier to work with. So moving back to the score tool. So it generates, our final results are from our new predicted values, from our 20%. So you can see what these scores are, right? So with our, this new data that we had with our 20%, it kind of predicted what our Ys would be. And the reason why you also would like to split it up is that you have the actual, data to compare it against. So to find our error, we just, do our score that we predicted minus the actual. And then you can see it here, our error is quite high. So we can look at each data point. The error for our first one is 479, negative 3,000. Our third data point is actually not too shabby. But this is actually what we would expect with a model that doesn't, with an R-squared value that's so low. So what would this tell us is, we would want to use a different model. We would explore other options. So that's generally the idea of how you would do a linear regression model. I have another question that's asking about the p-value. So if you look in these results here, looking at the p-value, the way you test significance with the linear regression at least, is you do a t-test. So that's what these t-values are. And they're kind of related to our p-value. So you do a test against this t-value to see how significant it is. Now, in relation to the nested test result, you'll see that it's a p-value and it talks about greater than f. So it just does a different type of test to test significance. So it's just testing against this value, and the significance is still the same. So yeah, that's generally our linear regression model tool. I can pause for a moment if anyone has any questions specifically about this. I have a few notes about the decision tree and lift charts, which I can get into, but I'll hold off if anyone has any quick questions or wants me to explore something further with this model. For instance, with the regularized regression. Tick-tock, tick-tock. Okay, cool. So I'm receiving nothing, so I will continue on to talk about a little bit more about decision trees. So just a quick note about decision trees. So this technically is not regression. So when we talk about regression, we talk about more of like a trend line that you develop. So that's why linear regression, logistic regression has that word regression attached to it. The decision tree builds more or less a tree that it's made decisions off of, aptly named. So yeah, again, so it uses a binary response, so yes or no's. That's how it does its splits. If you look at the static report that it'll give out, you can see it splits based on yeses and no's, ones and zeros. So it's similar in the logistic regression in the sense that our target variable will be yes or no. But of course, it can also be used for continuous targets, which is why you could also use it for this. And the same thing, it has 3 outputs in terms of the new form of the tool that we have. It has the object, static PDF type of report, and an interactive one. But yeah, not regression, but can be used in the same way to predict values. And then the one thing I wanted to talk about was our lift chart. So when you do, so for instance, in our linear regression tool, or example, we found that our linear regression model probably wasn't the best model to use. So let's say we used our decision tree, and now we wanted to compare them. Which one of our linear regression model or our decision tree, or even our stepwise model, is most effective? Which one do we want to use in the final process? Oh, sorry, quick. Are you saying that for this data, there's no real significant findings? So the significant findings we can get, let me go back to it. Sorry to interrupt, guys, about the lift chart. So our score, our error is horrendous, right? Our R values are bad. But what can we find out from this this model is that in terms of linearly, sorry, I'm bad at speaking. Our income is very important. Our income is pretty significant in determining how much a household spends. So you can always find something that you can kind of use and that'll tell you something else when setting up a different type of model. So in terms of this, so that's what all of these other things can tell us. So yeah, let's see what else we can find out of here. So yeah, well also, it can also tell us that these don't have so much significance. So that's why I do all these tests, to kind of make sure, double check, and kind of prove to yourself what does have value and what doesn't. For instance, and there is a kind of an art to it as well. So if you remember back, so let's say religion was part of this, this data set, this variable set, and we included it. And it turned out that religion was actually pretty significant to determining someone's money spent at restaurants, which actually I guess could be possible. But let's just say, religion actually, when we logically think about it, it actually has zero, it does not make any sense that someone would spend money based on what religion they are. Again, example, hypothetical. But our test shows that, it actually is. And maybe it just coincides with, just a really odd coincidence. That's where you would know, you kind of have to infer and look at it and do this kind of eye observation to know that, you want to remove it. You want to get rid of that religion because we don't actually, it's like an outlier. We don't want to actually include it. So those are the other things that you kind of tell when you go through these test-ins and testing out different models and stuff. I hope that answers your question. And yes, religion could be a proxy for other attributes. It could influence other things, but for the sake of this example, I just want to say, just assume it's totally weird and doesn't make any sense. So yes, back to our lift chart. So we have a bunch of different models. Again, this is different than the nested test, where we're not comparing similar models. We're not comparing a subset of one model. We're comparing different types of models. So we have our linear regression. We have our logistic. We have our decision tree. We have our stepwise. And we will run all of these together to see, which model of this is best. Which one can get us our results the quickest. One thing to note, though, it's only for binary classification. So meaning, only the models that use yes and no's, ones and zeros. So actually, linear regression could not be used with the lift chart. And simply, how would you kind of do it in Alteryx? You kind of union all the tools together. So what does that mean? Just to cover all my bases. It's just an object. So when we would union them together, our stepwise and linear regression would just be along one data record. So they all process through the lift chart at once. So that's how it would work, and that's how it compares all of them. And then what it outputs is kind of like a static report that we can look at. So we get this plot, and we get this gain, what's called the gains table, and our area under the chart. And just to quickly go over it, or I'll try to break it down simply, is we want to look for which model gets to 100% up here the fastest. And the way it does it is it scores it itself. So it takes these models and gets the predicted models, and then it compares those to the actual values. So similar to when we scored it here, right? We can reorder. Oh wait, where is this? We can reorder our score. So these are our predicted. We can reorder these to match up with our actual values, and then we compare them to see if at what point do they match. So you do it at the first 10%, then the next 20%, then the next 30%, 40, 50, and you see how much of our predicted values match up with our actual values. And you do that until you can capture all of the actual values. So that's how fast, does it actually get there. So when you graph it, the fastest one to get to 100% would have the greatest area under the curve, meaning it would be the best one. So in this case, our stepwise model would be the best. I hope I explained that well enough. And so actually, before I get into any extra things, does anyone have any questions? Because this is the end in terms of the general bulk of the knowledge. I'll sit here for a minute or two. Anything with the linear regression? What do we got? Stepwise, nested test. Can I interpret the Gini coefficient a bit? So the Gini coefficient, it kind of, how can I explain this? It's, so it's created through the lift chart. Oh, and then, okay, so more explanation on the lift chart. So in terms of the Gini coefficient, I'll just say it's just a measure of statistical dispersion. And in terms of how the deciles are sorted, so how you compare them, is you would take your predicted values. So let's go back to Alteryx real quick so I can show this. So what you would do here is you take your predicted values and then you would resort them to be, how would you sort them? Oh, well, it wouldn't work with linear regression, as I said. It works with yeses and nos. So what you're actually comparing is, how many yeses it found and how many nos it would find. So in this case, you would sort, and when you do the score tool with binary classification, you actually get probabilities. So like 80% that it was a yes, 70% it was a yes. So with that score, with these percentages, you would actually reorder them to be the highest probability to the top and those probability to the bottom. So that when you take the first 10%, you're taking the top 10% of the highest probabilities that were scored yeses. And then you can compare those yeses to the first 10% of the actual yeses. And then, so that way, you want to see, the highest predictions would actually have all the yeses. Anything else? Again, I just want to say, the workflow I used and the data is on that community post where the live training is. If you guys want to explore it a bit, it is there for you. I'll also be posting this PowerPoint. It has some extra notes in it, presenter notes that could be useful for you guys if you want a little bit more explanation about it. So I'll just move on from here, just some extra stuff. Any Alteryx designer training, you know, we have, like I said, future live trainings that we'll get into. And of course, explore community. It's great. I love it. Apparently our users love it, so that's cool. And of course, if you have issues, you can contact my team, support. This is, how you can learn. So we have community, like I said, Alteryx support group. It's great. I love it. We have Alteryx Academy, which is, what you guys are here for. Super fun. It's actually my first one, so thank you guys for attending. And, technical support. So if you guys run into weird errors or something strange is going on, you're not really sure what's going on, you can't find the source of the error, feel free to contact us, and we'll get you guys squared away. Let's see, what else do we got here? Oh, man, it's freezing on me. Okay, there we go. And yeah, let us know how we did. After this, you'll be directed to a survey. You can read. Take a moment. Let us know how we did. Hopefully I did a good job, guys. And thank you. Hopefully you guys will succeed like the Eagles, which is my hometown, and will not fail miserably like Tom Brady in his dying quest to get that thing. I have another comment coming in. So cheers, Mark. Mike. Yeah. Well, if you guys don't have any other questions about logistic regression, feel free to, ask about anything else in my life. I enjoy nice various topics of music. But yeah, I'll just leave a couple minutes. If you guys want anything else, I'll stand.